All right, thank you so much for the introduction. Thank you all for being here. So the last time I was here, I spoke about how we were able to replace some JavaScript computations with WebAssembly and ended up speeding up our app by tenfold. Today, I wanted to explore how WebAssembly in a serverless approach can also be equally useful. And so before I get into that, just a bit of info about myself. So my background is a mix of software engineering and bioinformatics. I'm currently a bioinformatics software engineer at Invitae, which is a genetic testing company about 10 minutes this way. And we're also hiring, so if you're looking for a great company to work with and a really awesome mission to work at, then check it out. Last thing I wanted to mention is that earlier this year, I published a book called Level Up with WebAssembly, which, according to me, is a practical guide to getting started with WebAssembly. So anyway, how many of you here have heard of WebAssembly before? Okay, so pretty much all of you, which kind of makes sense. How many of you have had a chance to tinker with it a little bit, even just a tutorial? Okay, quite a bit, nice. How many of you had a chance to use it in your applications? Okay, I always get 5, almost exactly. I don't know how this happens. Cool, so you're in the right place. Let's talk about WebAssembly. So what is WebAssembly anyway? For those of you who are new to this meetup, here's how I like to think of WebAssembly. For the last 2 decades, really the only choice we had as a language to use in the browser has been JavaScript. And sure, we had things like Flash and ActiveX, but those weren't really supported in all browsers equally and had several security flaws until 2017 when WebAssembly came onto the scene. And so from a very high level, I like to think of WebAssembly as just another language that you can run in the browser. Now, some of you might be thinking, well, I actually like JavaScript. I don't want to have to learn yet another language. So what does this language look like? Well, here's a hello world example in all its glory. There's a lot of things going on there, and it's not too clear what's actually happening. But thankfully, WebAssembly, a little bit like actual assembly language, doesn't have to be coded directly. So most people will take existing code written in languages like C, compile it down to WebAssembly, and then run it in the browser. So that's the second point, is that it's really a compilation target for languages like C and C++ and Rust. There are other languages with some support, but these are the ones that have the best support so far. And so really, practically what this means is that you are able to take existing code written in these languages and run them in the browser, which is not something that we've traditionally been able to do very well. So what? Here are a few examples of when you might see WebAssembly used. One thing you could do with WebAssembly is port existing desktop applications to the web, and this has been done with Doom, Google Earth, and AutoCAD, which are all ginormous C++ code bases that nobody really wanted to rewrite from scratch JavaScript, understandably. And so WebAssembly helped them transition to the web. But you can also port non-graphical command line tools to the web. Things like SQLite, JQ, and even Python are all written in C, and you can compile them and run them in the browser. And these are examples of playgrounds that you can give your users to try out the command line interface. Now, you don't necessarily have to port an entire application either. You can also take a more targeted approach, and this is the one that's been taken by 1Password with their plugin. eBay, they had a barcode scanner written in C. They compiled to WebAssembly. They got order of magnitude speed up. Same thing with FastQBio, which is a genomics tool I mentioned the last time. We also saw a pretty big speed up by turning to WebAssembly. And so all these are examples of applications that you can, of how you can use WebAssembly on the web. But as it turns out, WebAssembly can also be useful outside the web. And so one simple example is you could take a WebAssembly runtime and execute the WebAssembly files outside of the command line. Seems simple enough. But you can also import somewhat WebAssembly modules from languages like Python. Essentially, you're relying on some external compiled module to help you carve out more features than you originally had and do it in a way that is more efficient. Another thing that's people have started to work on is WASI, WebAssembly System Interface. And the idea there is that when you're running something outside of the web, say on the command line, how do you manage permissions for things like files and sockets and ports, right? In the browser, that's pretty straightforward to figure out. And so WASI intends to be a sort of standard interface around requesting permission for these things. And the thing that I will focus on today is serverless WebAssembly, where the idea is that you give a cloud provider some WebAssembly binary, and you want them to execute that code anytime, let's say you call an API function. So in all those use cases, the things that make WebAssembly awesome is being able to reuse existing code. In some cases, you might be able to speed up your applications. The sandbox nature of WebAssembly makes it really nice for the serverless model, as we'll see in a bit. And the portability, this idea that you can take one WebAssembly program and run it anywhere that supports a WebAssembly runtime. So instead of just diving into the serverless, I wanted to take a sample application and show you how you would build it using a variety of architectures. So the app I'm going to show you does data analysis. And I want to show you how you could actually run the analysis in the browser or on a server or in a serverless fashion. Cool. So the app in question, some of you might remember this from the last time I spoke. So this is an application where you drag and drop some raw DNA sequencing data. The details aren't so important, but the idea is that when you drag some files in there, it will parse out the file inside the browser, make a few computations to give you a sense for the data quality, so you can look at it at a glance. So how do we build a tool like this? Well, assuming we have a browser and a server, the most obvious approach is just to have the UI, the interactivity be in JavaScript, and then the server could do the analysis. Now, in our case, for genomics tools, there's a ton of C libraries that do these kinds of analyses. So let's say that we have our trusted library that we execute upon getting an API request from the user. And that works, but it also means that you have to essentially upload chunks of your data onto the server so that the server can process it so that they can give you back the result, which isn't that great. What if you know that the files are on the user's computer? So let's do the analysis in the browser. And so what this would look like is that the UI would be in JavaScript, but then the analysis, let's pretend we don't know about WebAssembly. You could essentially rewrite the C library into JavaScript and hope that it works. And this is actually what we had done at the time. And this has a lot of benefits, namely, say what? Okay, so namely, there's no servers. So deploying this is super easy. It works offline. However, this required a rewrite. So we have to take this code base, write it in JavaScript, and hope that it does the same thing and behaves the same way. And also, it was quite slow. And so this is where WebAssembly comes into the picture, where you can say, we don't have to rewrite these tools anymore. We can compile them to WebAssembly and just use them directly in the browser. And so I'll get to the punchline for number 3, which I talked about in my previous talk, where we're able to see 20x speed up. And you can check out the talk on the WebAssembly channel. But so the pros and cons here is that now you have a much faster interface, and you can reuse existing code. And essentially, just every time that library updates, you can compile it and start using it. The downside, though, is anytime you use WebAssembly, you're adding complexity no matter what. WebAssembly isn't the easiest technology to work with. And so this does add complexity to your code, to your build process, and so on. So then let's explore what it would look like to have a serverless architecture where, let's say we know that for a particular use case, the data is not on the user's browser or a user's computer, but is actually in the cloud. And so from that point of view, it kind of makes sense that you'd want to, with UI and JavaScript, then do the analysis in a serverless manner. And what we could do is just run the WebAssembly module, the same one that we run in the browser. And so how do we do this? How do we actually implement this green box? So I wanted to talk about 3 different approaches that you could take. The first approach, probably the simplest one, is go to your good old cloud compute, your favorite cloud provider, and you can create a Node.js serverless function. Because it's JavaScript, you could just instantiate the WebAssembly and run it, and it's fairly straightforward to set up. However, it's also quite slow because of most of these serverless implementations use some sort of container-based implementation, and spinning up Node isn't trivial either. And so you end up spending hundreds of milliseconds waiting for the function to spin up. And then you also have the cold start problem, where if you haven't executed that function in a while, it's going to take even longer to spin up. Another approach that's taken by Fastly is to say, let's not run things in containers. Let's run things directly in a WebAssembly engine. So this is Lucid, a WebAssembly runtime that they created. And essentially, you give them a WebAssembly binary. And when you call the API function, they execute it for you. And because they can use WebAssembly as the foundation of their isolation layer, it means that they can run thousands of customers' requests in the same process. And what that means then is the initialization time is now in the microseconds, which is completely unheard of in the serverless world. And so this isn't in production yet, but you could try it out at Fastly Labs. And they have an IDE, and you can deploy it, and it stays up for about 15 minutes. And then you can play with it a bit. Today, I'll focus on the third approach, the Cloudflare workers, where the idea is that what you're going to use to execute the function is V8, our favorite brand, tomato juice. Cool. Oh, he got it. Okay. So V8 is Chrome's engine, and there's this functionality within Chrome called isolates, and the Cloudflare blog goes into more details about this, but the idea is that it lets you isolate 2 execution processes such that you could do the same thing that Fastly is doing, is running multiple consumers' requests at the same time. And so you end up with a much faster initialization time. We're not talking microseconds, but still in the single-digit millisecond, which is still extremely fast. So why does any of this matter? Well, here are 2 reasons. The fact that WebAssembly has a very sandbox nature by definition lets these cloud providers more easily isolate the workers, meaning that the initialization times are very small. And so we basically get rid of the cold start problem altogether. But the other thing is that if a serverless provider supports WebAssembly, it means that they also support all the other languages that you can compile to WebAssembly. And this is not something that you've traditionally been able to do, launch a C++ Lambda function, right? You would have to compile it, include the binary, and so on. So going back to our FastQ Bio application, if we take the model and use Cloudflare workers, this is what it looks like. You see on the right, it's sending a whole bunch of parallel post requests. And every time it gets some data from the worker, it updates the graph. So I kind of wanted to give you a URL where you could all try this, but I figured most of you don't have DNA sequencing data readily available. So instead, here's another example. It's a worker that just computes the MD5 hash of a message. So if you give it test, it gives you this. If you give it hello, it gives you this. And it works really fast. And just to give you an idea of how you can build something like this. So I went on GitHub, found an implementation of MD5, looked pretty complicated, but it was written in C, so I compiled it to WebAssembly using the Wrangler tool, which is a tool that Cloudflare built that makes it a lot easier to deploy things to the Cloudflare network. And that's pretty much it, really. Let me see if I have internet access. I do. So I can, type more stuff, and you can see that it responds really fast. Okay, where do my slides go? Cool, so if we go back to this architecture list, now, in addition to having no servers, because we're not managing them ourselves, we also have the notion that this is more lightweight on the end user's computer. You're not, making their laptop catch on fire if you do too much analysis. But also it means that you know exactly what kind of environment your worker is running on. And so if you're doing data analysis, you can kind of push it to analyze more data without having to worry about the end user computer equipment. On the other hand, of course, the downside is that now you're making API calls over the internet. So this will slow down the process, and it doesn't work offline. So then what's the best approach? And as with a lot of things in technology, there isn't a simple answer, I'm afraid. However, if you think about the question of what's the best approach, you can start asking questions. Namely, first of all, do I need WebAssembly for my application? And if I do, should I run it in the browser or on the server? So when should you use WebAssembly? Well, would your application benefit from being able to reuse existing code written in C, C++, Rust, and all the others? Would your application benefit from possibly replacing slow JavaScript computations with WebAssembly? If so, that might make sense. On the other hand, if your application is sending data back and forth across the JavaScript and WebAssembly boundary, WebAssembly would not work very well in that case. And also, if you're dealing with files like we're doing here, what does the access pattern look like? Do you need to load the entire file into memory? Or can you sample randomly from the file as we did? Or can you go to a certain byte position using an index so you don't have to load the whole thing? So let's say you figure out, okay, WebAssembly might be right for me. Should I run it in the browser or on the server? The first question is typically, if you're running a code that depends on some data, where is that data located? If the user provides you the data from their browser, it might make sense to just do the analysis there. If the data is on a server or somewhere in the cloud, then it might make sense to run it on the server instead. The other questions you could ask is, well, is my process compute intensive? Is it going to fry my user's computer or not? And that tells you whether to run it in the browser or not. The other thing to keep in mind is that when you're running a serverless function, you're always going to run into quotas. So you're going to have quotas as to how long your function can run, how much memory it can use, CPU, storage, and so on. So you have to kind of take that into account to see if it's feasible for your application. And then you can start asking, well, would a combined approach make sense? So for the FastQ Bio example app, one approach we could have taken was to run a preview of the analysis in the browser to give the user something to look at right now while we spin off the analysis in the cloud in the background, so that by the time the user is starting to see some data, the cloud is already getting back to us. And so we can kind of do a mixture of those approaches. Okay. So if you're interested in learning more about WebAssembly, I am extremely biased, but I've heard good things about this book. And, and I recently added a guide on serverless WebAssembly. So it talks about how to launch WebAssembly on Google Cloud, Azure, Cloudflare, Fastly, AWS, all those. But I also have a whole bunch of free articles and tutorials that you can check out if you're interested in learning more. In particular, this one is about serverless WebAssembly. And with that, I want to thank you all very much.
So you have time for questions. Just raise your hand. I'll come with you with the mic.
Sorry if I'm missing the point on this, but so like the third model you showed where we pass data back to a serverless instance. I'm not sure why would we want that instance to compile to WebAssembly again. I'm kind of missing that because if it's running C there anyway, and then we just pass the data back or whatever, I don't see why we'd want.
Oh, you mean this one?
Yeah.
Right. So the trouble is you can't directly run C in a serverless function. You would have to like.
You can run like Rust and Go and whatnot, but not C, I guess, right?
Can you run Rust directly? Because
okay, maybe I'm mistaken on that. I'll check it.
Because I feel like with languages like that, you would have to compile it to a binary and then zip up the binary and then deploy it. But it's kind of why we took that approach.
Okay. All right. Thanks.
So this is somewhat a follow-up on that question. Are all C, I'm not sure what the state of C compilation to WASM is. Are all C programs essentially compilable to WASM?
I don't think I can say yes to that, but.
So a service that took C and compiled it automatically to WASM and then deployed it in a serverless environment would not be possible.
I mean, it could be. Sorry, yeah?
Yeah, so the answer is yes, you can compile all of C to WASM. Oh, that works.
Huh. Okay. So there you have it. For me, I found that in a lot of applications, you might not. There are some parameters that you need to set when you're compiling to WebAssembly that you can't always have an automated solution that guesses what those parameters are. So for example, things like what type of file system are you using, threading, all sorts of things like that that aren't easily inferable. So yeah.
Thanks for the interesting talk. So in your bullets there for should I use WASM, there's this JS to WASM translation one.
Yes.
Is that because of the difficulty of encoding your JavaScript data into WASM? And do you think some of the proposed extensions to WASM, like interface types or things like that, could help there?
So one of the challenges there is that if, say in our case, the data is actually on the user's computer as a file. And so we have to pass that data over to the WebAssembly one way or another. And so what we found was that, obviously the more data you pass in, the slower it is, but also the more you output, the slower it is. And so the way that we got to that 20x was by basically reducing how much data we're returning to only have the actual information that we need. So the best application would be basically a computation where you take a small input and return a small input. But in our case, we're passing in a big input and getting back a big input. So that's where the challenge is.